If the world were simply linear, we would have no need for calculus. Although linear equations are exceptionally helpful, and there are numerous situations where we use them, there are also a number of situations where we must use something beyond the linear equation. We must use some model that is not linear. And if it's not linear, it means that the change in y is not constant as x changes by 1. We have a changing slope. This lecture, lecture number 8, will look at two polynomial type of equations that we'll use as models, and this is the quadratic, the second degree, and the cubic, the third degree equations. First, we're going to look at the quadratic. And it turns out there are many, many physical situations in which a second degree equation is useful. For example, the force of gravity is proportional to the inverse of the square of the distance between the two bodies. So as you double your distance, you don't halve the gravitational force. Your gravitational force is 1/4, so there's a square involved. This is called the inverse square law, which also operates in terms of light intensity. As you double the distance away from the light, the intensity of the light is 1/4. As you halve the distance to a light, you quadruple the intensity of that light. The area of a circle, and how many times do we use circles in the real world? The area of a circle is proportional to the square of its radius. The distance a body travels in free fall, that is under gravity with no other force applied to it, is equal to 1/2 gt squared, where g is the acceleration due to gravity and t is the time. So we have a quadratic equation. The lift of an airplane wing is proportional to the square of the airplane's speed. You might notice that faster airplanes generally have smaller wings. When an airplane slows down to land, it puts out its flaps. Those flaps extend the area of the wing because the area of the wing has to compensate for the slowing down. Remember, if the slowing down is squared, again, we need a sufficient area to maintain the lift so the airplane can land. The F-14 Tomcat, when it takes off, has straight wings because it's at a slow speed. And when it lands, it has straight wings. But in flight, its wings are swept back. This provides less lift, but again, the airplane is going much faster when it's in flight than when it takes off or lands. And because we're dealing with the speed squared, it can reduce the area. Sweeping back the wings reduces the area. It also reduces interference between the wing and the air it's traveling through. For hundreds of years, a general solution was sought for the quadratic equation, ax squared plus bx plus c equals 0. Earliest investigation we know about occurred in 628 in India. The mathematician's name was Brahmagupta, and he sought, but unfortunately did not find, to our knowledge, a solution. In 825, the Arab mathematician Al-Khwarizmi worked on a solution. We know he worked on it, but again, he did not find it. Finally, in 1637, again, that's a very important year. We've heard that year on a number of different lectures. René Descartes, that French mathematician, produced a geometric solution to the quadratic equation. Again, he was using the Cartesian plane, the geometric representation of algebraic equations to solve. And he solved the quadratic in general geometrically. This was the beginning of what is known as analytic geometry. So some people would say that René Descartes is the father of analytic geometry, the use of geometric representations to analyze solutions to algebraic problems. Eventually, the quadratic formula for the solution of the general quadratic equation, ax squared plus bx plus c, was found. That solution is x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Investigation of the quadratic solution continued throughout the 17th, 18th, and into the 19th centuries. In 1851, James Sylvester gave the name discriminant to the b squared minus 4ac. Looking at the quadratic formula, you will notice that the b squared minus 4ac, the discriminant, is inside the square root. If b squared minus 4ac is positive, then we have two real roots. Again, they may not be rational, but we have two real roots. So we'll have two answers to the quadratic. Negative b plus the square root of b squared minus 4ac over 2a, and negative b minus that square root over 2a. If the discriminant, b squared minus 4ac, is 0, well, the square root of 0 is just one number, 0. We wind up with a single solution, negative b over 2a. If b squared minus 4ac is negative, then the square root of that discriminant will be an imaginary number, and our answers will be complex. That is, they'll have an I in them, as well as a real part. And this was important because it discriminates the type of solution and therefore is called a discriminant. In a short while, when we look at the graphing of a quadratic equation, we'll see that it further tells us something about what the graph looks like, specifically where the turning point of that graph might be. In fact, let's go ahead and take a look at the general equation where we're graphing a quadratic y equals ax squared plus bx plus c. Again, this is a second degree quadratic equation because the highest power term is the ax squared. The lead coefficient is a. If a is positive, the shape of the graph of this equation goes up. If the a is negative, the graph goes down, and we'll see why shortly. Okay, let's take a look at the graph of a general quadratic, and that is, this graph is called a parabola. You know, this parabola is going up, and this parabola, therefore, has a positive lead coefficient. A is greater than 0. If a had been negative, the direction of the parabola would be reversed, and it would sort of empty down. Notice the vertex, the turning point, is indicated. This is a vital point. This is where the parabola starts from going down to going up. And of course, if you had an upside down parabola with a negative a, the vertex would be where it's going from increasing to decreasing. Obviously an important part, especially if you're dealing with a model. Notice there is a dashed line down the middle of the parabola. That is an axis of symmetry. The right side of the parabola would fold directly onto the left side of the parabola, and therefore every point on the left side of the parabola has a mirror point on the right side of the parabola. Now, how can we graph this parabola? Well, there's a very easy procedure for graphing a parabola if you have the equation y equals ax squared plus bx plus c. The first step is to find the vertex. Okay. The vertex is obtained by solving for x equals negative b over 2a, where again b is the coefficient of x and a is the lead coefficient. Once we have the negative b over 2a, we have the x value, we replace the x in the original equation with that number, and we solve for y and plot the point x comma y. That is the vertex. Then we get the y-intercept. Remember, the y-intercept for a linear equation was the value of y when x is 0. In fact, the y-intercept for any graph of any type of equation is going to be the value of y when x is 0. Well, certainly when x is 0, ax squared is 0, and bx is 0, which leaves us with the y-intercept equal to c. So the point 0c will be the y-intercept for any and every parabola for the graph of y equals ax squared plus bx plus c. We already mentioned about the symmetry of a parabola, which means the y-intercept will have a mirror point, a point at the same y value on the opposite side of the vertex. And that point is easy to plot. We now have probably 3 points, a vertex, a y-intercept, and the mirror point. We then find the x-intercepts. The x-intercepts are the value of x that make y 0. We already have the quadratic formula, which tells us how to solve ax squared plus bx plus c equals 0. And we solve and we get 2 values possibly. Again, that's where the discriminant comes in. And when we get those 2 values, we can plot those two values on the x-axis, and they should be mirror points. If the first 4 steps in our process is not sufficient to allow you to graph the parabola to your satisfaction, then simply plot more points. How would you plot points? Very simple. Take any value of x you like, plug it into the equation, come out with a y, plot the point, and then you can plot its mirror point. When you have sufficient points, you can draw the parabola. Okay, the question now is, what about this discriminant, and how does it help us graph the parabola? Well, we know that if the discriminant is positive, there will be 2 real solutions, and therefore there will be 2 x-intercepts. So we know that the parabola will actually cross the x-axis twice. And if it's an up parabola, the vertex will be below the x-axis. If it's a down parabola, the vertex will be above the x-axis. What if the discriminant is 0? Well, if the discriminant is 0, that means there's only one solution, negative b over 2a. That should ring a bell. That is the value we use to find the x for the discriminant. Oh, sorry, the x for the vertex. And if the discriminant is 0, there's only one solution. There's only one x-intercept, and that is the vertex. So the parabola just touches the x-axis once. What if the discriminant is negative? We said that means we have complex solutions. Since the graph we're using is for only real numbers, no complex numbers appear on the graph, and therefore there's no place on the x-axis where the parabola can cross. And therefore, if it's an up parabola, it is strictly above the x-axis. If it's a down parabola, it's strictly below the x-axis. Let's look at some uses of the parabola. The first use we're going to look at is something we already mentioned, and that is a body in free fall. A body with an initial speed and no other force applied to it other than gravity. Specifically, we're going to look at an object that is thrown from the Earth up into the sky, and once it's released, it simply is at the force of gravity, and that's it. In this particular situation, we're going to throw this object up at a speed of 40 meters per second. The equation for this model is y equals negative 5x squared plus 40x. The negative 5 is the negative g, and the x squared is the t squared we talked about earlier. In meters per second on Earth, the gravitational acceleration is approximately 10 meters per second. The plus 40x is simply the velocity at which the object is released, 40 meters per second, times x, where x is the time in seconds. Let's go to the TI-83 and see what we can learn from the graph of this model. And here is that graph. This is the graph. It's a parabola of negative 5x squared plus 40x. Notice it's a down parabola because the lead coefficient is negative 5. The vertex, which is located here, is at x equal to 4. Again, using the minus b over 2a, negative 40 over negative 10 equals positive 4. What that says is 4 seconds after this object is launched, it reaches its maximum height. That height happens to be equal to 80 meters because we replace x with 4 and we get negative 80 plus 160, which is 80. So the vertex is at 4, 80. Again, meaning that the object, 4 seconds after it's thrown from the ground, has reached its maximum height of 80 meters. And again, once mentioning again, the lead coefficient is negative, we have a down parabola, because obviously that rock or object, ball, whatever we're throwing, is going to return to Earth. The y-intercept, of course, is at 0. Because when x is 0, that is at the instant the object is thrown from the ground, we have a height of 0. And you'll notice the y-intercept over here is at 0, 0. And since there has to be a mirror point, there's another point over here at 8, 0. And that point is when the object returns to the Earth. It returns to the Earth at the end of 8 seconds. So therefore, we have the complete path. Anything beyond this would not make any sense unless when it landed in a well and continued traveling down towards the center of the Earth. But suffice it to say that this is what's called a ballistic trajectory. The word ballistic should sound familiar. Perhaps you've heard of the ballistic missile, or in watching a police drama, you see the use of ballistics to solve a homicide. Well, that ballistic missile becomes ballistic at the moment when the last engine shuts off and it's nothing more than a nose cone traveling through the atmosphere, acted upon only by gravity. A bullet fired from a gun, once it leaves the gun with an initial velocity called the muzzle velocity, it is strictly under the direction, the force of gravity. And the path of that bullet, which is a parabola, is called a ballistic path. The path of that missile, which is a parabola, is called a ballistic path. And in fact, anytime you have anything thrown, kicked, shot, or anything else into the air with no force acting upon it other than gravity, you have a ballistic path. A thrown baseball, a kicked football, a hockey puck fired off a hockey stick, an arrow fired from a bow. These are all ballistic objects because they travel in parabolas generated by the influence of the Earth's gravity. There is another example or another method of writing a quadratic equation. And this is y equals a parentheses x minus h close parentheses squared plus k. A is still the lead coefficient and indicates through its positive or negative nature whether the parabola is up or down. H is the x coordinate of the vertex, while k is the y coordinate of the vertex. We're going to use this form of the equation to look at another set of data. This is data having to do with the population density of the United States, generated from census data since 1790. Let's go back to the TI-83 and look at this data. And here is a graph of that data. The x-axis is the year, the y-axis is the population density of the United States. Population density is obtained by dividing the population by the area in square miles. So that would be population per square mile. It's obvious from the graph that the population density of the United States has been increasing over time. The earliest data, this point right here, is for 1790, the year of the first census. The latest point at the very top is for 1990, which is the last data we have at this time. Now, a couple of interesting things about this graph. In general, as I said before, the population density has been increasing. But there are 3 times when the population density actually decreased. For population density to decrease, one of 2 things must happen. Either you lose people through unfortunate large-scale death or immigration out of the country, or you gain a great deal of area without gaining people. So let's examine, from a historical perspective, the 3 intervals in which the population density of the United States decreased. The first is from 1800 to 1810. The second is from 1840 to 1850. And the third, which is a very slight decrease, is from 1950 to 1960. Do you know why? Can you explain the reason for these deductions or reductions in population density? Certainly there were no great wars where a vast percentage of the population died or tremendous disease spread or something. Then it must be somehow we gained some land. 1800 to 1810. A little history trivia question. What happened? How do we gain land? Well, we should know we're coming up in a few years on the bicentennial of that event, the Louisiana Purchase, where the United States, for a small amount of money, received from France vast amounts of empty territory, very few people. And remember, American Indians were not counted in the original part of the United States as population, and therefore there were just a couple of hunters or traders out there. Huge area, almost no population gain, and the population density went down between 1800 and 1810. What happened 1840 to 1850? There were actually two events that caused us to gain tremendous area with minimal population increase. The first was Texas, which was a republic from 1836 to 1845, became a state. Again, Texas is a very large state, and at the time, 1845, the population was rather small. Also, the Mexican-American War was won by the United States, and as a victor, we took a good chunk of Mexican territory that is now the states of California, Arizona, New Mexico, Utah, Colorado, etc. So again, a large large area increase with very little population, which led to a decrease in population density. And of course, 1950 to 1960, the state of Alaska was admitted to the Union, and Alaska, then as now, has huge land area and a very small population base. Now, the question comes about of greater importance than answering these historical trivia questions is what kind of model can we approximate these data with to allow us to possibly predict what the population density might be in the year 2010 or 2020. We wouldn't want to go too far out. Well, obviously, we could simply take an equation, and we have an equation here. Here's the equation. Basically, what you see is a form of A. A is here 0.0018. X minus H. The H is the vertex. We've chosen to use the year 1790 as the X value for the vertex, squared, plus 4.5. 4.5, you will recall, was the population density of the United States in 1790. So what we've done is we've used 1790, 4.5 as our vertex, the year and the population density from the first census. The 0.0018 is obtained through experimentation until we got a good match. And let's see if it's a good match. Here is our equation. You'll notice it is a rather good match for the data. You may say, well, I think I can do better. And if we wanted to take the time, we could experiment on the graphing calculator using various values of A until we got a parabola, and obviously the right side of an increasing parabola, that matched up to the data to your satisfaction. The key thing is that we have a quadratic model that will allow us to predict population density in the near future. Again, we would not want to use this model to predict the population density of the United States 50 or 100 years from now, because that would be extrapolating too far out. Events could occur that would cause the model to change. But in the near future, this could be a very valuable tool. For example, people who think that the population of the United States was too low could look at the population density and realize that although the population density in our major cities is quite high, the overall population density of the United States is still rather small, and there are vast areas where we could have people live if they'd want to live out in West Texas, for example. I'm not sure about that, but it's out there, and certainly the average population density in the United States would be valuable information, and the model would give us that for years into the future, as long as we're in the near future. Now, there's another type of polynomial equation that can be quite useful, and that is the cubic equation. The cubic equation is of the form y equals ax cubed plus bx squared plus cx plus d. And you'll notice now the lead coefficient is still a. It is the number in front of the x cubed. The y-intercept, of course, is going to be d, because all the terms contain x except d, and therefore when x is 0, y will be d. The general solution for the cubic equation ax cubed plus bx squared plus cx plus d equals 0 has been sought for thousands of years. The first known attempt to solve a cubic was done by Babylonian mathematicians in the year 1600 BC, or possibly slightly before that year. That was a long time ago. Of course, they didn't find the solution. Omar Khayyam, known to some as a poet and tent maker, but was indeed a great mathematician who used geometry, studied geometric solutions to cubic equations in the year 1100. In 1545, Girolamo Cardano, the Italian mathematician, demonstrated a solution to a special form of the cubic equation, x cubed plus bx equals c. Again, this was not a general solution, but a general solution to a very specific type of cubic equation. Credit for the discovery of the general solution of the cubic equation was given to Évariste Galois, a young Frenchman who accomplished this in the year 1832. Galois was a brilliant young mathematician who had some real tragedies in his life. One of the tragedies was he died at the age of 21. Galois was so bright that the greatest mathematicians in France at the time couldn't understand his work and therefore, in their egocentrism, thought he was wrong. And he was never accepted into the club of mathematicians, despite the fact that he was well ahead of the most brilliant mathematicians who existed in Europe at that time. He also was involved in politics. In that time, there was a real terrible thing going on in Paris between the folks who wanted a king and the folks who wanted a republic. And for some reason, he got involved in this, and many books indicate that he was set up. But either way, he was caught in a, let's say, delicate situation with a married woman whose husband challenged Galois to a duel. And he could have probably left the area and stayed alive, but being too much of a man to do that, he fought the duel, knowing that he would die because this husband happened to be an excellent shot, and Galois was too busy solving math problems to work on his marksmanship. So the night before the duel, Galois stayed up all night writing in his journal and writing all the thoughts in his mind about mathematics. The journal was left in a box in an attic for 50 years, and when it was discovered, mathematicians took another 50 years to figure out everything Galois was saying. This was one bright young man. Okay, so he had the general solution. Now, we want to see what's the purpose of this cubic equation and why would we want to solve it. So let's talk about a set of data. And to talk about a set of data, let's go to the TI-83. And here are the data. The x-axis is the years 1981 through 1994. The y-axis represents the number of high school soccer players in thousands in the United States. What makes this a candidate for a cubic equation? What you see is in the years before 1988, the soccer players' numbers were growing, but growing at a rate that was decreasing. While in the years after 1988, the growth pattern was such that the growth was increasing at an increasing rate, typical of a cubic function. Now, the question is, the year 1988 was important, and it's called an inflection point. And the question that has to be asked is, what happened before 1988 or in 1988 to change the growth pattern of the number of soccer players? When asked about this, many people suggest something to do with the World Cup or Pelé. It's very interesting that the answer to the question, what caused this inflection point, has nothing to do with soccer. It is Title IX, which caused high schools and colleges to have to equalize the money spent on women's sports and men's sports. The increase in the growth rate of the number of players playing soccer from year to year was caused by the addition of girls' teams at the high school level. And therefore, with all these girls' teams being added, we have an increase in the rate of increase, thus the cubic function and thus the inflection point. By the way, the inflection point is quite interesting. There is at least one example I know of a merchandising company, and is a retail chain of stores, that used the inflection point, recognizing when the growth of a product they were selling was increasing at a decreasing rate after increasing at an increasing rate. At that point in time, they stopped ordering those products. Other stores, first seeing the growth in this other store's sales, started ordering the product. They lost money, the other stores, because the growth was about to decrease. This one store went on to a new product and is now the top marketer in this country. Perhaps you know who this is. So we could see that quadratic and cubic functions have a tremendous ability to help us model the real world, to solve problems, and to make predictions. The next lecture, Lecture 9, will talk about the power of another type of function, the exponential function. The power of exponentials are next.